All right, so today we're talking about phase changes. Phase diagrams are the topic for today. Again, this is on exam 3. This will not be on exam 2. Okay. Where we're going in this next unit is all about energy and changing state and transfer of energy. Okay, that's the next big theme. So we're actually going to take a break from stoichiometry for a little while. Woohoo! Take a break from some of those other things that may have been driving you crazy. And we're going to completely switch gears for this next unit. It's going to be all about energy. It's going to be about matter. It's going to be changes of state, all that good stuff. Okay. So let's just review states of matter, right? Liquid, solid, liquid, gas. Right? What's happening in these processes? We're going from solid to liquid, right? We're calling that melting, fusion. And then we're going from liquid to gas, vaporization, or if you're going the other direction, condensation. All right, and then notice look at the difference in energy here, right? It takes less energy to melt than it does to vaporize, right? This is something that we're going to see in our calculations very soon. We're going to be calculating the amount of energy it takes to melt something, the amount of energy it takes to vaporize something. The amount of energy it takes to vaporize is way more than it is to melt, right? Think about why. Particles in the gas phase are way higher in energy than particles in the liquid phase. So where does the gas get its energy? Well, you put that energy in vaporization, right? Which is why this arrow is so much bigger. Now, if you're going the other direction, right, you get all that energy back when you condense, and then you get that energy back again when you freeze. And if you go straight from gas to solid, right, that's deposition. And if you go straight from solid to gas, that one's sublimation. And I showed you a video of sublimation of CO2 demo that I did with my kids back at the beginning of the semester. So what we're talking about today are phase diagrams. Okay, these are phase diagrams. These are completely qualitative, meaning there's no math. All you've got to do is interpret them. Okay, so a generic phase diagram that I will hand to you will be, no, the recording isn't going to capture this, but that's okay. Right? It's got some sort of Y shape, and it can be varied more this way or more this way. But it's going to be blank. Okay? You guys need to know where the solid phase is, where the liquid phase is, and where the gas phase is. Right? This is solid. It's the one closest to the Y-axis. Then liquid, and then gas. Right? It spells slug, S-L-G. Solid, liquid, gas. Okay? So I will hand you a phase diagram, but I'm not going to label solid, liquid, vapor, okay? You need to know where those are. So start here, going clockwise, solid, liquid, gas, or solid, liquid, vapor, okay? What's being plotted on the x-axis is temperature, and it's either going to be in degrees Celsius or Kelvin, and what's being plotted on the y-axis is pressure, and it's going to usually be an ATM. Atmospheres is what the metric system of pressure is, right? We're not going to use PSI. That's not a metric unit. Okay, so temperature and pressure will obviously be labeled for you, but these phases will not. Okay, so you just need to know where the solid phase is, the liquid phase is, and the gas phase is. Okay, there are some other points on this curve that we need to talk about. So this one way up here at the top, way up here at the top. Okay, so notice when you're up here, you are at high pressure, right, and you're at high temperature. So beyond this point is called a supercritical fluid, where we're not really interested in is it really a vapor or is it really a liquid? We can't really tell. So beyond that point, which is called the critical point, it's the line between these two becomes too blurred. Okay, so it's because you're at way high pressure, you're at way high temperature. Right? So we're calling this the supercritical fluid beyond that point. Okay, that's what the critical point is. So on your generic one that you drew on your page, right? If you drew it in your notes, you would just pick some point way out here, high pressure, high temperature. Okay? That's not going to be something that happens at room temperature, right? Room temperatures, about right there. Right? All right, here, this is the vaporization / condensation point, right? I say both because it depends on which way you're going. If you're going from liquid to vapor, that's vaporization. Right? If you're going from vapor to liquid, that's condensation. Now, notice it is specific. The normal boiling point, right, boiling, vaporization. The normal boiling point occurs when the vapor pressure equals what? We talked about this on Monday. When the vapor pressure equals the what pressure? Atmospheric pressure, right? So we are really, really darn close to 1 atmosphere pressure. Right? That's the pressure we're feeling right now. It's really, 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 really close to 1. Okay? So that means that the normal boiling point is the temperature where the pressure equals 1 atmosphere. Does this make sense? So if I said, all right, what's the boiling point of this liquid? You would read the temperature where the pressure is 1. Right? So here for this substance, it'd be 100. Okay? So that's the normal boiling point or the normal condensation point, right? Depending on which direction you're going. We typically talk about it as, a boiling point, because we're usually adding heat to liquid to get to vapor, right? So this would be the normal boiling point. Again, it is specific because it's the temperature where the vapor pressure equals atmospheric pressure. So you can't just pick any old temperature, right? You need to find, okay, there's 1, and then find the temperature at that, right? If you're at high elevation, let's pretend that you're at the top of a mountain where the pressure is, 0.7 atmospheres. And I'd ask, okay, what's the boiling point here? You'd find 0.7 and read it off, right? Okay. Do you understand how elevation plays a role in this? Right? Normal would be at 1. If you're at some extraordinary circumstance, you figure it out based on that. Here's the freezing and melting point. Right? Again, based on this 1, right? The temperature and the pressure of 1. Okay, and again, we call it melting / freezing depending on the direction we're going. On that interface between solid and liquid. And then this last one right here, where they all intersect, is called the triple point. It has a unique scenario where you have all 3 phases. It's called the triple point. Okay, triple points right here where they all intersect. So these kinds of problems are just interpreting a phase diagram. Okay? There's no math to do here. You just qualitatively read the chart. Now I'm going to go back to a question that you asked earlier in the week about the liquid water in the vacuum. Right? I wasn't ignoring you. I just thought, hey, this would be a perfect time to talk about this. Let's pretend that we're at 1 atmosphere, right? And then this is actually the phase diagram for water. We can tell it's water because water's kind of tilts back like that. I'll show you some other ones as a comparison in a few minutes. Well, let's pretend here's water, right? And we put it in our vacuum chamber and we slowly remove all the gas. So what do we have at vacuum? The pressure is 0, right? So if you're at here and you suction out all the gas, right? Your pressure goes down to 0, so you would have that vaporization occur. Now, I'm not so sure. The part that I'm kind of questioning is it going to look like typical boiling? Because that was what you asked, right? Is it going to boil? And I guess it would depend on the rate that it's removed, right? Like how quickly. I would imagine it would based on how fast your vacuum is at pulling it out. But yeah, once you drop the pressure out, right, based on the phase diagram, it's going to go from liquid phase to vapor phase. I just think the question is going to be how quickly that will occur. Does that make sense?
Yeah.
All right. So here's one for you to interpret. Now, I know this one's a little bit harder to see just because you're sitting far away, but do your best. Try your best and approximate what's the normal boiling point, what's the normal melting point for this substance. Just take your best educated guess. When I give you one on paper, obviously you can draw on it, make it a little easier. Now, we haven't talked about this as being on the top of a mountain or in the bottom of a deep, deep canyon, right? So what pressure are we going off of as our reference pressure? 1, right? Normal boiling point, normal melting point. So then all we need to know is, okay, which line do we look at for boiling point? Which line do we look at for melting point? Which one do we look at for boiling? Here, 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 where? The interface between which two colors? Blue and what? Solid, liquid, gas. So which one would it be?
Solid.
The solid and liquid, right? This one will be sublimation, right? If we're going from liquid to vapor. So it's the solid liquid line at 1 atmosphere. So if we do our best, reading across, and then the temperature at 1 atmosphere pressure, I don't know, I'm guessing maybe 140, 41, somewhere in that neighborhood, right? If I gave you one on an exam, obviously I'd give you a better scale that you could read a little more easily. Okay, what about, so that one, the solid liquid, that one's melting, right? Solid liquid, that's melting. What would the boiling point be? What interface? The liquid and gas would be the boiling point, right? So we keep going. And down, I guess maybe right at 200, right? That's the liquid gas interface at 1 atmosphere pressure. Do we agree on this one? How to do it? All right. So let's try another one. If we're at 1 atmosphere, we're at 2 atmospheres pressure and 110 degrees Celsius, what phase am I in? Solid, right? Because that's about right there. Okay, what pressure and temperature give me the triple point for this substance? Or sorry, 0.8. It's probably about 0.8. Yep, I'd agree. And then temperature, maybe 120, somewhere around there, 118. I don't know. Good. So there's the answer for part A, right? And then there's the answer for part B. Okay, here is another one. Let's do this one together. 1 atmosphere and temperature of 20. Now this scale is awful, right? I would never give you a scale, -78, -56, all the way up to 31, right? That's just a lousy scale. So do your best to approximate. This 1 atmosphere pressure and 20 degrees Celsius, what phase are we in?
Yes.
Right, we're in gas, because 1 atmosphere and 20 would be about right there-ish. If the pressure is then increased to 50, what phase are we in?
Probably liquid.
There's a good chance we're in liquid, right? Because there's 73 and there's 5. Again, that scale's awful. I wouldn't give you a scale that bad, but let's just assume we're about right there. If the temperature is then lowered to -100, what happens? We're in solid, right? We're over here. All right. So I've got a handout for you, and it's on the screen as well. And it's about water, because water is a unique substance, as I've alluded to several times already this semester, from an intermolecular forces standpoint, a density standpoint, and physical property standpoint. Water is just a really unique substance. And so these are 2 phase diagrams. The one on the left is carbon dioxide, one on the right is water. Right? So you notice water kicks back for the solid part pretty significantly, right? And the one I showed you at the beginning was also water, just scaled a little differently. This one's in Kelvin, the one I showed you a few minutes ago is in Celsius, but it's not that much of a difference. Now, this paragraph right here is what I really wanted to draw your attention to. Normally, the solid liquid phase line slopes positively to the right, as seen in the diagram for carbon dioxide. However, for other substances, notably water, the line slopes to the left, as the diagram for water shows. This indicates that the liquid phase is more dense than the solid phase. This phenomenon is caused by the crystal structure of the solid phase. In the solid forms of water and some other substances, the molecules crystallize in a lattice with greater average space between molecules. Right? We've already talked about this too. Remember when I showed you pictures of water and it freezes? It actually spreads out, right? The gaps between the H2Os in that crystal lattice, which is kind of a hexagonal shape, it actually spreads out. So if you take the same mass and you spread it over a greater area, its density goes down, thus resulting in a solid with a lower density than a liquid. Because of this phenomenon, one is able to melt ice simply by applying pressure and not by adding heat. So if we're right here, right, and we want to melt ice, right, so what are the two ways we could melt this? Well, we could increase the pressure, right, because it slopes back. Notice that'd kick us right here. So we could increase the pressure to melt ice. And then, of course, obviously, we could heat it as well. And this is a significant thing to talk about now that we're coming into winter and like hockey season and all that, right? Because how do ice skates work? Ever thought about ice skates? Look at the bottom of the ice skate, right? It's a very, very, very small surface area that all your weight is being applied to. So what is the ice skate actually doing? It's increasing the pressure, and that's what's melting the ice, and that's how you're skating around, right? It's pretty unique. That's one of the unique things about water. So in other words, you don't have to, have heated skates, right, when you're skating around, because your pressure is enough to do the job, right? You can melt it by increasing the pressure. That's pretty unique, right? That's one of the unique things about water. You can't do that for CO2, right? You wouldn't be able to do that. If you increase the pressure, I mean, you'd have to, I don't think you could, right? You just wouldn't work for CO2 especially. So that's where we're going to stop on this.